Hello students, now we'll be solving memory-based questions of GATE 20. For more video solutions on GATE 20, subscribe to our channel and don't forget to click the bell icon for instant notification.
Hello students, we are proud to announce that we are the first institute to provide video solutions for today's GATE paper. To download the question paper and answer keys, please click on the description given below. Okay. So in this session, today we'll solve questions from Thermodynamics set 2. Okay. Very good. So as you can see, the first question goes like this. This is a 1-mark question from the set 2. If a reversible Carnot cycle operates between temperatures of 27 degrees centigrade and -3 degrees centigrade, then COP refrigeration by COP refrigerator by COP heat pump is dashed. So in this question, they are asking you to find out the ratio of coefficient of performance of a refrigerator and a heat pump. Okay. Now the main keywords to concentrate on are reversible Carnot cycle. This is a keyword. See, all the hints in any GATE question paper is given in the question itself. If you read the question or if you properly analyze the question, you will find all the hints to how to solve the problem. Okay, very good. Let us see. The keyword here is a reversible Carnot cycle. Now we know any reversible Carnot cycle, if it is operating, between two temperature limits, its COP will be same. It doesn't matter whatever is your working material, working substance, or whatever the engine is. If it is a Carnot cycle and it is operating between two temperature limits, then its COP will be same. Of course, we are talking about a refrigerator and a heat pump. Very good. Now we know the COP of a Carnot refrigerator. Remember, I am saying a Carnot refrigerator. The COP of a Carnot refrigerator, I'll take this as COPR. COPR is equal to T lower by T higher minus T lower. Very good. What is this TH? TH is the higher temperature of the working cycle, whereas the TL is your lower temperature of the working cycle. The values are given to me, but I'll write it later on. Very good. Nice. No problem at all. So this is COP of the heat pump. Again, we know for a Carnot heat pump, the COP is given by T higher minus T lower. Very good. Now you see, we know the formula for a Carnot refrigerator and a Carnot heat pump. I have written down the formula. Now what are they asking in the question? They are asking you the ratio. Very good. They are asking the ratio of your Carnot refrigerator and the Carnot heat pump. So let me see. Carnot COPR by COP heat pump. Very good. This is equal to T lower by T higher minus T lower divided by T higher minus T lower. Nice. Now see, these two terms are common. So I can cancel these two terms off. So what I am left with? I am left with COP of refrigerator by COP of heat pump. COP of heat pump is equal to T lower by T higher. Now let me see what are the values of lower temperature and higher temperature is given to me. The lower temperature value here is given as -3 degrees centigrade and the higher temperature value is given as 27 degrees centigrade. But if we want to use these temperatures in this equation or in this form, we have to convert it into absolute temperatures. So first of all, I'll have to convert my temperatures which are given in degrees Celsius. I'll have to convert them into Kelvin. Very good. See, let us see how we can convert this. All of us know that the degree centigrade can be converted into Kelvin by simply adding 273. So let me see, T higher is equal to 27 degrees centigrade, or this will be equal to 27 plus 273. I'll get 300 Kelvin. Very good. Now the lower temperature, I'll get -3 plus 273. I'll get 270 Kelvin. Nice. No problem. Now we have everything we require to find out this ratio. Simply I'll put the values. T lower is equal to 270 by T higher is equal to 300. So the value of the ratio of COP refrigerator by COP heat pump. Very good. COP heat pump we will get as 0.9. Very good. So this is your answer. Okay. So the question goes like this. For an air standard diesel cycle, you are given 4 options over here. Heat is supplied at V is equal to constant. That means heat is supplied at constant volume. Then in the same option you have heat is rejected at P is equal to constant. That means at constant pressure. Then option B we have heat is supplied at constant volume and heat is rejected at constant volume. Okay, here in both the heat supplied and heat rejected, the volume is kept constant. Then in option C we have heat is supplied at constant pressure and heat is rejected at constant volume. Fine. And option D we have heat is supplied at constant pressure and heat is rejected at constant pressure. Very good. Now let me see where are the hidden clues over here. The hidden clues over here is diesel cycle. Very good. Now to answer this question, I'll have to know what is a diesel cycle. Very good. I'll not take much time. I'll just draw your PV and TS diagrams for the diesel cycle. I'll just draw the PV and TS diagrams. This is a very easy question and it can be very easily answered. TS diagram. Now, the diesel cycle from process 1 to 2, it is isentropic compression. Very good. From process 1 to 2, it is reversible adiabatic compression, or we can say it is an isentropic compression. Right. Very good. Sorry, this is 1 and this is 2. No problem at all. Then in process 2 to 3, the heat supply is taking place in your diesel cycle, and in that process the pressure is kept constant. Always remember students, your diesel cycle is known as the constant pressure cycle and your Otto cycle is known as the constant volume cycle. It all depends on what you are keeping constant while supplying the heat. For diesel cycle, the pressure is kept constant while supplying the heat. So your graph will be something like this. Very good. No problem at all. Very good. So your graph will be something like this. Very good. 3 and 4. Right. So 3 to 4 is your heat supply process. Nice. And 3 to 4 is the heat supply process QS, and 4 to 1 is your heat rejection process QR. If I draw it on the TS diagram, I'll get the diagram something like this. 1 to 2 is again your isentropic compression. Then 2 to 3 is constant pressure heat addition, and 3 to 4 is constant volume heat rejection. Very good. No problem at all. Here you can see the curve of your constant volume. Here V is equal to constant and here P is equal to constant. The heat supply is taking place at constant pressure and heat rejection is taking place at the constant volume. Very good. Now you can see the constant volume curve is always the slope of your constant volume curve on a TS diagram is more than the slope of your constant pressure curve on the TS diagram. So your diagram will be something like this. Anyway, that is not our main motive. The main motive here is to find out at what is being kept constant when your heat is being supplied and what is being kept constant when heat is being rejected. Now we can easily see in the graphs that heat supply is taking place at constant pressure and heat rejection is taking place at constant volume. So if I match with my options over here, I'll see that option C has heat supplied at constant pressure and heat rejected at constant volume. So my correct option here will be option C. Okay. So here is the next question. So let us see what is the question saying. Okay, this is a 2 marks question. Okay, remember this is a 2 marks question. So let us see what is the question saying. Air is contained in a frictionless piston cylinder arrangement as shown in figure. Okay, this is the figure given to you. Let us see what is given in the figure. We have air enclosed by a piston. This is your piston, and we have a spring over here. The spring is not touching the piston, okay, but it is 8 centimeter above the piston. Then we have stoppers in the cylinder which are 8 plus 8, that is 16 centimeter above the piston. This is your equilibrium condition. Fine. We are given some data over here. What is given to us? Atmospheric pressure is equal to 100 kilopascal. Then initial pressure is 105 kilopascal, and the area of your piston, AP is nothing but the area of the piston, is given as 300 centimeter square. Okay, fine. Next, what is done? Let us see. Heat is added and the piston moves slowly until it reaches the stop. Very good. When we are adding heat to the system, what will happen? As it will gain heat, the piston will start moving upwards. Very good. And as it will start moving upwards, what it will do? Up till 8 centimeter, it will move freely. Then the spring will start exerting some additional pressure on the piston. Very good. Now let us see what are they asking us. The spring is a linear spring with a spring constant. This K is nothing but spring constant is equal to 12.5 Newton per millimeter. Very good. The work interaction is dash joule. Okay, very good. So we are being asked to find out what is the work done by the gas. Very good. Let us see. No problem at all. We'll see how to find this out. First of all, the work that is done by the gas is divided into 2 parts. The gas will do work in 2 parts. One part is against the atmospheric pressure, and remember, atmospheric pressure plus this piston is also going to exert some force on the gas. Very good. So the first part against which your air will do work is against the atmospheric pressure and the piston. That is up till this 8 centimeter. The next part, the second part that the air will do work is against your spring. This spring will also resist the expansion of air. That's why as air expands up till the stop, it has to do work against your spring also. So if we can find out, if we individually find out the 2 different works, we can easily find out the total work. Now, there are certain very important things. One thing in this question is, this is a very good question. They have employed or they have given a trick. This is a type of a trick they have given. What they have given is, once they have given atmospheric pressure and the initial pressure is given to you. What is the initial pressure? This initial pressure is when this piston is in equilibrium when the air was not heated. That means under equilibrium condition, the pressure inside the air was 105 kilopascal. But the atmospheric air is 100 kilopascal. So where is this extra 5 kilopascal coming from? This is coming from the piston. The piston will also, due to the weight of the piston, an extra pressure will also be exerted on the air. Very good. So the pressure that we have to consider, the pressure against which the air will work is this pressure. Is this pressure and not this pressure. Against this pressure also, this is the atmospheric air, but this P initial, this consists of both your atmospheric pressure as well as the pressure due to the weight of your piston. Very good. So the first part of the work done can be easily found out if I find out what is the work done against this pressure. So let me see how to find this out. Force we know as it is. Force is nothing but equal to pressure into area. Now we'll have to take this pressure. So this is 105. Very good. 105. No problem at all. 105 into, let us see what is the area given to me. The area given to me is 300 centimeters square. Very good. No problem. 300 divided by 100 into 100. Why I am dividing this by 100 into 100? Because it is given to me in centimeter square and I have to take it into meter square. Okay. So if I solve this, I'll get the force is equal to 3.15 kilonewton. Very good. So this is the force that is acting, or this is the force against which this air has to work while expansion. Okay. We are not considering the spring. Remember, we'll consider the spring later on. First of all, we are considering only the work done against the air pressure and the weight of the piston, the pressure due to weight of the piston. Very good. So this is the force. So let us see what is the work done against this force. This is given by F into D. Now, against this air pressure and the piston's weight, this whole gas will do work from this point to the stop. That means it will move, this will move through a distance of 16 centimeter. So we know force into distance, work is given by force into distance. So 3.15 into, it is 16 centimeter. So this will be 0.16 meter. So the work done will get as 0.504 kilojoule. Now they are asking me the answer in joule. So I'll take out, or I'll find out this answer in joule. So if I'll get 504 joule. Very good. This 504 joule is nothing but the work done against your atmospheric air and the weight of the piston. Now let us see, we'll have to, the second work done by the air is against the spring. So we'll have to find out what is the work done against the spring. Now, if we take a look at this diagram, we'll see that as the piston moves towards the stops, the spring gets compressed by 8 centimeter. Now, the spring constant is given to me, and also it is given to me over here. This is a keyword. This is a linear spring. Very good. We are given that this is a linear spring. So, for a linear spring, the work done is given by, half K into X square. So, K value is given to me. K value is equal to, okay, this is given in 12.5 Newton per mm. So I'll have to convert it into Newton per meter. So if I convert it into Newton per meter, I'll get this as 12.5 into 1000, or I'll write this as into 10 to the power 3. X is nothing but the distance through which the spring is compressed. Here, if I take a look at this diagram, the spring is compressed by only 8 centimeter. So, converting it into meter, we'll get 0.08 square. Very good. No problem. So, if I solve this, I'll get the work done as 0.04 kilojoule. Very good. Now, solving this, I'll directly get my answer as 440 joule. Very good. I'll get this as 40 joule. So the total work done is nothing but the summation of these two work dones. So if I solve this, I'll get it easily. Total work done. This is equal to 504 plus 40. 504 plus 40. I'll get this as 544 joule. Very good. So this is the total work done by the air inside this piston cylinder arrangement while moving from here towards the stops. Okay, so here is the next question. Let us see. This is a 2 marks question. So let us see what is the question saying. Keeping all other parameters constant, the compression ratio of an air standard diesel cycle is increased from 15 to 21. cutoff ratio is 2 and the value of gamma is given to be us as 1.3. The difference between old and new efficiency values in percent is dash percent. Okay, so they are saying that all other parameters are kept constant. Now let us first see what is the efficiency of a diesel cycle given by any air standard diesel cycle. The efficiency is given by new diesel cycle is equal to 1 minus 1 by R to the power gamma minus 1 into RC to the power gamma minus 1 divided by gamma RC minus 1. Very good. So this gives me the air standard, this gives me the efficiency of your air standard diesel cycle. Now, as according to the question, in the question what are they saying? That all other parameters, very good. So this becomes the keywords for you. All other parameters are kept constant. What are they changing? Only the compression ratio. Very good. Only the compression ratio is increased from 15 to 21. Otherwise, all parameters are kept constant. That means what? If I take a look at my expression for efficiency, I have only two other parameters other than my C. This is the compression ratio. Here you have the compression ratio. This R is nothing but the compression ratio. RC is your cutoff ratio. And gamma is your adiabatic index. Very good. So all other things are being kept constant. Only your R is being changed from 15 to 21. So let us see how, first of all, we'll find out your old efficiency. Then we will find out the new efficiency. But since this term is kept constant, I'll first try to find out the value of this term and then I'll make the changes. Very good. So let us first see what will be the value of this part. RC to the power gamma minus 1 divided by gamma RC minus 1. Very good. So RC is already given to me. RC is nothing but the cutoff ratio. RC is given to me over here. Very good. RC is given as 2. Nice. No problem. RC is given as 2. Very good. So once I have the RC, I'll put the value of this RC as 2 and the value of gamma is given as 1.3. So 1.3 minus 1 divided by 1.32 minus 1. Very good. If I solve this, I'll get the value. Solving this, I'll get the value. This term is equal to 1.125. Very good. 1.125. This term has got the value of 1.125. Now, if I want to write my diesel efficiency again, new D, this I can write as 1 minus this whole term. I have got the value as 1.125. Very good. I'll write this as 1.125 divided by R to the power gamma minus 1. Beautiful. Now see how easy this problem becomes. Simply I have to first, when I am finding out the old efficiency, I'll put the value of the diesel or compression R to be equal to 15. For the old, new, old, if I simply put the value of R is equal to 15, I'll get the old efficiency 1 minus 1.125 divided by 15. Gamma minus 1 is nothing but 1.3 minus 1. So I'll get this as 0.3. Very good. So if I solve this, I'll get the old efficiency to be equal to 0.5. Nice. No problem at all. I'll get it as 0.5. Or this, if I convert into percentage, I'll get this as 50%. Nice. So old efficiency is now known to me. Now, once I find out the new efficiency, I can easily get my answer. And okay, fine. I'll take this as efficiency N. So again, 1 minus 1.125. These will remain constant. What will change is the compression ratio. So now, what has the compression ratio become? Now the compression ratio has changed to 21. So instead of 15 here, I'll put R equal to 21. R equal to 21 to the power 1.3 minus 1. Very good. If I solve this, I'll get the new efficiency equal to 0.55. Nice. No problem at all. 0.55, or I'll get this as 55%. Now, what is the change? They have asked the difference between old and new efficiencies. So, the difference between old and new efficiencies is new N minus new old. So, this is equal to 55 minus 50. I'll get this as 5%. Very good. So, what has happened? Your efficiency has increased by 5%. Okay, so here is the next question. This is again a 2 marks question. Let us see what is the question saying. 1 kg of air in a closed system undergoes an irreversible process. Look at here, it is an irreversible process. From P1 is equal to 1 bar, the temperature is also given, T1 is equal to 27 degrees centigrade, to a final state of P2 is equal to 3 bar, T2 is equal to 127 degrees centigrade. For air, the characteristic gas constant is given to you as 287 joule per kg per Kelvin, and the adiabatic constant gamma is given as 1.4. Very good. The change in entropy of the air is dash joule per kg per Kelvin. Okay, very good. Now here they are giving you, the keywords are again the irreversible process. Very good. It is an irreversible process, remember, to a final state. Okay, the state has changed from state 1 to state 2. And they are asking you to find out the change in entropy of air. Remember, entropy of the air. Entropy of the air. Now we know the entropy is a property of the system. It is a property. Okay. So what will happen? The entropy change will remain constant. Remember students, your entropy is a property, but entropy generation is not a property. They are not asking you the entropy generation. They are simply asking you the change in entropy of air. Very good. If I want to find out the change in entropy of air, I'll simply replace my irreversible process with a reversible process, and I'll get the entropy change of your air. For any gas, we know for any gas, the entropy change is given by S2 minus S1. Of course, it is an ideal gas. For any ideal gas, the change in entropy is given by S2 minus S1 is equal to Cp ln T2 by T1 minus R ln P2 by P1. Very good. So this gives me the change in entropy of any ideal gas. Now as we know, air can be treated as an ideal gas. So I'll take this equation to find out the change in entropy of air too. Very good. So let us see. The pressure is given to us. The temperature is given to us in degrees Celsius, but here we will have to take the temperature in absolute terms. So let me first convert my temperature into absolute temperatures. So T1 is equal to 27 degrees centigrade. So plus 273 if I do, I'll get 300 Kelvin. Nice. And T2 is equal to 127 degrees centigrade. If I add 273 to this, I'll get this as 400 Kelvin. Very good. Nice. No problem at all. Now we have found out the temperatures in absolute temperature terms. Very good. I'll simply replace the values. We know from our knowledge that the Cp for air, the specific heat at constant pressure for air, is equal to 1005 ln T2 we have already seen is equal to 400 and T1 is 300 minus the R value for air is given to us. The R value is given as 287 over here. The R value is given to us. Very good. No problem for that. 287 ln P2. Definitely P2 is also given to me. Here is the P2, 3 bar. And P1 is also known to me somewhere over here. Very good. I have it over here. P1 is equal to 1. Now, simply it is a matter of solving these numerical terms. If I solve this, I'll get this equal to 289.12 minus 315.3. Very good, 315.3. Solving this, I'll get this, the entropy change to be equal to minus 26.18 joule per kg per Kelvin. Very good. So this is the entropy change of your air. Okay, students. So here is the next question. Moist air at 105 kilopascal, 30 degrees centigrade and 80% relative humidity flows over a cooling coil in an insulated AC duct. Insulated AC duct. Very good. Saturated air exits from the duct at 100 kilopascal and 15 degrees centigrade. The saturation pressures for water at 30 degrees centigrade and 15 degrees centigrade are 4.24 kilopascal and 1.7 kilopascal respectively. The mass of water condensing out from the duct is dashed gram per kg of dry air. So this question belongs to your psychrometry chapter, okay, and it is a 2 marks question. So let us see how we can solve this question. Very good. Now just by going through the question, I can see that we are asked to find out the water that is condensing out from the moist air. Very good. Now we know what is the humidity ratio or specific humidity, that is omega, is nothing but it is mass of water by mass of dry air. Very good. So the specific humidity is nothing but mass of water by mass of dry air. Now as the dry air flows or as the moist air flows through the duct, the mass of dry air in the duct remains constant. As air is flowing through the duct, suppose this is your duct. So this is your duct. There is no way for we do not provide any escape routes for the air. So what will happen is the mass of dry air will remain constant. Only what will happen when the coil condenses your water, the mass of water will decrease. Now we know your specific humidity is nothing but mass of water by mass of dry air. So whatever the decrease in specific humidity, that much will be the decrease in your mass of water, or that much mass of water, has condensed. So let us see how we can go about solving this problem. Very good. Now my first aim is to find out what is the specific humidity at condition 1, and then find out, that is at inlet of the duct, and then find out what is the specific humidity at exit from the duct. If I can find out what is the inlet specific humidity at 1 and what is the specific humidity at 2, very good. I'll draw the diagram in this manner. This will be much more helpful to you. Very good. I'll draw the diagram in this manner. This is 1 and this is 2. Now, whatever the specific humidity, the difference of specific humidity omega 2 minus omega 1, omega 1 minus omega 2, this will give me how much water condensed. This will give me the water. Omega 1 minus omega 2 will give me the water that has constants. So my first aim is to find out omega 1. Now let us see how we can find out the omega 1. At state 1, your relative humidity is given to us. Very good. 80% relative humidity is given to us, and at state 1, the temperature is 30 degrees centigrade and the pressure is also given to us. At this pressure, at this temperature 30 degrees centigrade, the saturation pressure is also given to us. Very good. No problem now. We'll see how to solve. We know phi, that is your relative humidity, is nothing but vapor pressure by vapor pressure under saturation condition. So omega 1, phi 1, that is relative humidity at state 1 is given to us. That is given as 80%. So I'll take 0.8 is equal to PV1, vapor pressure at 1, and the vapor pressure at condition 1, the saturated vapor pressure at condition 1 is given to me as 4.24. Very good. From here, I can find out what is the vapor pressure at condition 1, PV1. So solving this, I'll get PV1 is equal to 3.392 kilopascal. Nice. Once I have got this vapor pressure, very good. Once I have got this vapor pressure at state 1, I can easily find out my specific humidity at point 1. So specific humidity omega 1 is equal to, we can find it out from this formula, 0.622 PV1 divided by P total at 1 minus PV at 1. Remember here students, there is a very big difference given to us. The total pressure at state 1 is 105 kilopascal, whereas the total pressure at point 2 is 100 kilopascal. So your total pressure is also changing as your moist air is moving through the duct from point 1 to point 2. Very good. So from here, if I put the values, 0.622 PV1 we have just found out, this is 3.392 divided by the total pressure at point 1 is equal to 105 kilopascal minus PV1 is again 3.392. Very good. If I solve this, I'll get omega 1 is equal to 0.02076 kg vapor per kg dry air. Very good. I'm getting this in kg vapor per kg dry air. No problem at all. I can easily change it into gram. We'll see that later on. Next, my next aim is to find out the specific humidity at state 2. Very good. So let me see how I can find out the specific humidity at state 2. The clue again is hidden in the question itself. Let us see. Here saturated air is given to us. Saturated air means what? The relative humidity will be equal to 1. Whenever your air is under saturated condition, the relative humidity is equal to 1. So phi 2 is equal to 1. Here phi 2 is equal to 1. So again I'll use this formula. 1 is equal to PV by PVS. Very good. But at point 2, the saturation vapor, the vapor pressure under saturation condition is given as 1.7. Now since this is equal to 1, the relative humidity is 1, I'll get this as PV is equal to PVS PV2. Very good. I'll take this as 2 is equal to 1.71. Very good. 1.7 kilopascal. Very good. I have got this as 1.7 kilopascal. Once I get the PV vapor pressure at point 2, I can easily find out what is my specific humidity. Omega 2 is equal to 0.622 into PV2. Very good. No problem at all. Into PV2. P total 2 minus PV2. Very good. No problems at all. Now we have already found out the PV2. So I'll take the values over here into 1.7. The total pressure at 2 is given as 100 kilopascal. Remember, it is not the same as the total pressure in 1. Here it has changed from 105 to 100 kilopascal. So I'll have to take 100 minus 1.7. Solving this, I'll get omega 2 is equal to 0.10757. Very good. 757 kg vapor per kg dry air. Very good. No problem at all. Now I have got both my omega 1 and omega 2. Simply, if I want to find out how much water has condensed, so omega 1 minus omega 2, omega 1 minus omega 2, that is specific humidity at point 1 minus specific humidity at point 2. This will give me 0.02076, very good, minus 0.010757. No problem at all. So this is equal to, very good, 0.010110003. Very good, 10003 kg vapor per kg dry air. Per kg dry air. No problem at all. But now they are asking the answer not in kg vapor per kg dry air, but they are asking it in gram per kg dry air. So simply if I multiply this with 1000, I'll get in gram vapor per kg dry air. So multiplying it this with 1000, I'll get 10 gram vapor per kg of dry air. Very good. So your answer will be 10 gram vapor per kg of dry air. Okay. So this is the next question, and this is a 2 marks question, and this is from your power plant engineering. Okay. Basically this question is from the topic vapor power cycles. Okay, right. So let us see what is the question saying. In a steam power plant, superheated steam of 10 megapascal. Okay, 10 megapascal is the pressure. 500 degrees centigrade is expanded isentropically in turbine until it becomes saturated vapor. Very good. So it is expanded in a turbine where it becomes saturated vapor. It is reheated to 500 degrees centigrade at constant pressure. The steam then expands isentropically in the second turbine to a pressure of 20 kilopascal. Very good. The total work done in both the turbines. Okay, they are asking you to find out the total work done in both the turbines. Certain properties of your steam is given to you in a table. So this will be, of course, we'll be using this table to solve this problem. So let us see how to solve this problem. First of all, I'll draw the TS diagram, which will be very helpful for me. If I draw the TS diagram, it will be very helpful for me to visualize what is going on. Very good. This is TS, and here this is your steam dome that we have. Fine. So from in the first case, what is happening? Superheated steam of 10 okay at a high pressure, that is 10 megapascal and 500 degrees centigrade. It is expanded until it becomes saturated. Fine. This is point 1, and here we have the point 2 where it is just saturated steam. Very good. Now it is again reheated to 500 degrees centigrade. Right. No problem at all. We'll draw it in this manner. Again reheated to 500 degrees centigrade. Point 3. And then again expanded to a condenser pressure. Very good. It is expanded somewhere up to here, which is point 4. See, how do I know where the point 4 is lying? If I just take a proper look at point 3, where it is 1 megapascal and 500 degrees centigrade, I'll see that the entropy is 7.7621. And at the condenser, the value of saturated steam, where it is at the condenser, it is 20 kilopascal. The value of Sg is 7.9085. Now, this is of course 7.9085 is larger than this. This point is of course over here. This point is the saturated point. So since the point 4, at point 4 S is less than this, the entropy of your saturated steam at this pressure, that's why I come to know that my point 4 will lie in somewhere in my wet zone. It will lie in my wet zone. Okay. So first of all, let us see what are the given values, or what are the values that we can directly find out from the table. Okay. Then we will see what we have to find out. Now the very first thing is the steam, this value at point 1, the value of pressure and temperature are these. So it is directly given to us at 10 megapascal, 500 degrees centigrade. The enthalpy is directly given to us. So I'll directly write this. H1 is equal to 3373.6. 3373.6 kilojoule per kg. These are all given in kilojoule per kg, and S is given in kilojoule per kg per Kelvin. Due to space constrictions or space restrictions, I am just writing the values over here. Fine. Here I'll write the units also. Very good. No problem. So H2, let me see what will be the value of H2. H2 is just saturated steam. Your point 2 is lying on the saturation vapor curve. So it is just saturation steam at point 1, that this 1 megapascal and 500 degrees centigrade. Okay. Let us see. Okay. For this point 2, this is for superheated. This part is for superheated steam and this part is for saturated steam. For saturated, here at point 2, the steam is just saturated. So I'll have to take values from the saturated steam part. At 1 megapascal, the saturated steam, the value of Hg. I have to take this value of Hg since it is lying on the saturation vapor curve. Okay, so this value H2, this value will become H2. This is equal to 2778.1. 2778.1. Very good. Kilojoule per kg. No problem. Now, next is H3. H3 again lies in the superheated region. For that pressure and 500, and also it is said the vapor is reheated. It is reheated to 500 degrees centigrade. So at 500 degrees centigrade and 1 megapascal, the value of enthalpy is given as 3478.4 kilojoule per kg. Very good. Now I have got my 3 values of enthalpy. But now, as I have already explained to you, the enthalpy or the point 4 lies in your wet region. So to find out this, I'll have to first find out my dryness fraction. Once I get the dryness fraction, I can definitely find out what is the enthalpy at point 4 from this table. Very good. Now, how to find out the dryness fraction? See students, here it lies the trick. How beautiful this problem is. 3 to 4 is an isentropic process. See, all these clues are hidden over here. You see, here is the hidden clue to you. It is an isentropic process. For an isentropic process, the entropy will remain constant. Now, the point 3 is superheated at 1 megapascal and 500 Kelvin. The entropy value is given to us. For an isentropic process, the entropy will remain constant, and the entropy at point 3 is known to us from the table over here. So let me write this down. S3 is equal to, since it is a 3 to 4 is an isentropic process, the value of entropy at 4 will be equal to entropy at 3. So S3 will be equal to S4. The value, I'll get it from here. I'll get the value from this point. Very good. 7.7621. Very good. 7.7621 kilojoule per kg per Kelvin. Very good. So I have come to know the entropy S4. Now I know, and when a point is in wet state, S4 is equal to SF plus X Sg minus Sf. From properties of pure substances, this relation is known to me. So S4 value we have already found out, 7.7621. Sf value can be found out at point 4. The pressure is 20 kilopascal. At this point, the value of Sf is equal to 0.8319. Very good. 0.8319. Very good. Plus X. Sg value is equal to this one. Sg value is this one. 7.9085 minus Sf value 0.8319. Very good. So if I solve this equation, I'll get the value of X. Solving this equation, I get the value of X to be equal to 0.98. Nice. Once I have got the value of X, X is nothing but your dryness fraction. So once I have got the value of dryness fraction, I can easily find out the enthalpy at point 4. The enthalpy at point 4, H4, is given by enthalpy at, for the condenser, enthalpy HGF and HG. Okay, very good. So HF plus X, HG minus HF. Nice. Simply I have to put the values. HF is equal to this value, 251.38. Nice. 251.38 plus X we have just found out, 0.98. Then HG value is this one, 2609.7. 2609.7 minus HF is 251.38. Very good. 0.38. Nice. If I solve this, I'll get the value of H4. H4 is equal to 2562.5336. Nice. 5336 kilojoule per kg. Very good. Now we have got all the enthalpy values at all the points, point 1 and 2 and 3 and 4. Now the total work done by both the turbines, is equal to nothing but H1 minus H2. This is the work done for the first turbine plus H3 minus H4. This is work done by the second turbine. So I'll simply have to put the values over here. H1 is 3373.6 minus, no problem, minus H2 is 2778.1 plus for the second turbine H3 is equal to 3478.4 minus H4 equal to, just now we have found out H4, 2562.5336. Very good. Now simply if I solve this, I'll get the total work done by both the turbines. So solving this, I'll get 1511.37 kilojoule per kg. So this is the total work done by both the turbines. So students, I hope today's session has been helpful to you. Do not forget to subscribe to our channel. Also, please do share this video with your friends. Thank you, students.